Assalamu alaikum dear students. I welcome you to 12th lecture of probability and stochastic processes. So far we have covered elementary probability theory and its applications to discrete random variables. If you pick up a good textbook of probability theory, you will find that the contents are usually laid out in such a way that the discussion of discrete random variables goes hand in hand with discussion on continuous random variables. I have deviated from this approach and I have restricted myself to application of elementary principles of probability theory on discrete random variables. This is being done intentionally and with good intentions. From my experience, I have found that students usually get turned off if they have to deal with complex mathematical operations like application of differential calculus to distribution functions and other involved quantities early in the course. So they get tied up with application of differential calculus to the problems and its related functions, but they do not get a good feel of the principle behind all those mathematical operations. By restricting ourselves to discrete random variables and relying on interesting and real-world examples like rolling of dice, counting the number of people entering a restaurant, or finding the lucky winner in a game like Chak Alak or prize bonds, we can relate to the ideas of probability theory and its applications to real life problems. Once we have finished application of these elementary ideas to discrete random variables, I plan to go to continuous random variables and apply all these ideas to continuous random variables using differential calculus. So far we have covered topics like conditional probability, conditional distribution, joint distributions, marginal distributions, expected values, transformation of random variables, and expected values of transformed random variables, all applicable to discrete random variables. Let's continue with our discussion and cover these topics and a few more in today's lecture, and from next lectures onward we'll start our discussion of continuous random variables. In previous lecture we were working with transformation of random variables. You know the old concept where you start with a sample space and there is a function called random variable which takes points from the sample space and maps them to points on real line, and you assign probabilities to events that represent this random mapping being equal to a certain point or real line. You can introduce a second mapping which takes points on this real line and maps them to another set of points on another real line. Then you assign probabilities to these mapped points and they indirectly get their probabilities from the sample space. This mapping from real line to real line is just one of the possible mappings, and if this mapping is from real line to real line, then the domain and range both are real lines and this mapping is from R to R. There are further subclasses that this mapping can belong to. This mapping can be invertible, which means it's one-to-one. If this mapping takes a point from this real line and maps it to another point, then there is an inverse mapping which takes this point and maps it back to the original point. That is one-to-one mapping. So if the discrete random variable has a few finite points defined where it attains some value, then the next real line where this transformed random variable takes its values will have the same number of points. So there will be one-to-one mapping. Or this R to R mapping could be many to one, where many points on this real line get mapped to a single point on the second real line. So all these mappings allow us to work with the transformed random variable directly. And when I say work with, I mean finding the probability mass function of the transformed random variable, expected value of the transformed random variable, and similar quantities. There are many examples of one-to-one mappings or many-to-one mappings. For example, if x represents the random variable on this real line and the transformed random variable is y, then y is equal to 2x is a one-to-one mapping. Y is equal to 2x plus 3 is also one-to-one mapping, and y is equal to exponent of x, y is equal to e raised to power x, it's also a one-to-one mapping. And examples of mappings which are many to one could be y is equal to absolute value of x, or y is equal to x square, or y is equal to sine of x. Well, this sine of x could be one-to-one if the domain where x is defined is limited. But if the domain is unlimited, then this mapping y is equal to sine x is usually many to one. When you are dealing with transformation of random variables, you are not restricted to mappings which are from R to R. You can have other mappings. For example, if two random variables x and y are defined on some underlying sample space, you can take values of these two random variables x and y, combine them together and map them to a third random variable z, which is a real valued random variable. So you take points on 2D plane where x and y are jointly defined and map these two-dimensional vectors to points on real line. So this mapping is R2 to R. There could be other variations, for example R3 to R, and there could be pairs of mappings where from one random variable, one mapping maps to a new random variable, another mapping maps to another new random variable, and these two new random variables can be defined on a 2D plane. So there are all sort of mappings and groups of mappings which change the values and the associated probability values of random variables. We have talked about the inversible mapping, the reversible mapping, and have put it in a separate subclass. This type of mapping, which is reversible, is easier to deal with because it allows us to readily find the probability mass function of the transformed random variable from the probability mass function of the original random variable. If the mapping is many to one and it's not readily reversible, then finding the probability mass function of y, the transformed random variable, from x, the original random variable, is usually a little bit more complex. Let's extend our discussion of transformation of random variables with an example. We're going to take a random variable x, which is discrete and takes 8 possible values. The 8 possible values and the associated probabilities are drawn in the PMF of x as shown in this slide. Please note that we are not going to talk about the original sample space over which this random variable was defined. We'll just restrict our attention to the values this random variable takes and the associated probability values. So this random variable takes on values of -4, -3, -1, 0, 1, 2, 3 and 6, and associated probability values are either 1/15, 2/15 or 3/15, as you can see in the slide. Let's define our transformation, and this transformation is going to be a reversible transformation where y is equal to 2x plus 1. So if x takes on a certain value, then the transformed random variable takes on a value which is twice the value of x plus 1. If we fit all the possible values x takes into this formula y is equal to 2x plus 1, we'll get all possible values of y being equal to -7, -5, -1, 1, 3, 5, 7 and 13. Since this transformation takes random value x and transforms it to random value y, hence there are 8 values in random variable x and 8 values in random variable y. Remember, this transformation is one-to-one and reversible. So if x takes on a certain value x1 with probability p1, then the random variable y will take on value 2x1 plus 1 with same probability. So probability of x being equal to x1 is equal to probability of y being equal to y1, where y1 is 2 into x1 plus 1. You can fit all the values of x, get all possible values of y with same probability values getting assigned to the values of random variable y. This is shown in your slide, and you can see that the probability mass function of y is very similar to the probability mass function of x. The former is just an expanded version of the earlier. There is another way to get to the probability mass function of y. You know this is a reversible mapping, so you try to find the mapping from y to x, and this happens to be y minus 1 divided by 2. Then you want to find probability mass value of random variable y for a certain value y1. You take that y1, pass it through reverse mapping and get a point x1, where x1 is y1 minus 1 whole divided by 2. If this point x1 is one of the valid points where random variable x takes on some value, then the probability of y being equal to y1 is same as probability of x being x1. So there are two ways to find PMF of y. If the mapping is reversible, one-to-one, you just transfer these probability values to the transformed random variables new values, or you can take on collection of values of transformed random variable, pass it through the reverse mapping and see if the reverse mapping falls on a valid point, you get the probability mass function values. And if the reverse mapping does not get a valid point in random variable x, the probability of y being equal to that value is 0. In the slide, you can see the probability mass function of x on top and probability mass function of y below. The two probability mass functions have been drawn with same scale on the x-axis to emphasize the point that the values taken on by random variable x on top just get expanded in the random variable y. This happens because this mapping y is equal to 2x plus 1 is kind of expensive. It increases the values of x when it goes to y. It's possible to define a mapping which is reversible, one-to-one, but contractive. For example, y is equal to x over 3 minus 0.5. In this case, the random variable x, the values taken by random variable x will get squeezed when it reaches the random variable y. One more thing, you can see that the probability mass function values of random variable x go in a certain sequence. Small value, larger value, same value, to very large values, smaller value, and then to smallest values. And if you look at the PMF of y, these values occur in the same sequence but at greater distance from each other. This is because of the linear nature of this mapping, y is equal to 2x plus 1. If we had used some other kind of mapping, then these values which y takes may have some different relationship with the values of random variable x, or it's possible that there is no visible relationship between the values of random variable x and the values of random variable y. Let's take another example of transformation of one-dimensional random variable to one-dimensional random variable. But this time we are going to use a mapping which is not invertible. Let's take the same random variable we were talking about in the previous example, but this time we are going to use a mapping y is equal to x minus 1 absolute value of x minus 1. If you put in the values that x takes into this formula, you will see that the 8 values that the random variable x assumes get mapped to just 5 values. So certainly this mapping is many to 1. So how do you find probability mass function of transformed random variable y, which is obtained by this mapping y is equal to absolute value of x minus 1? You have to use that inverse mapping, where you pick a value of y and see through inverse mapping, which could be 1 to many, what are total number of points in x which get mapped to y, and then you add probabilities of all those points, and that will be the probability of y being equal to that point. If you use that, you can find the probability mass function for this example, and this new probability mass function for transformed random variable is shown in the slide. If you look at this slide, you will see that random variable x takes on 8 values as before, but random variable y takes on only values of 0, 1, 2, 4 and 5. Furthermore, the probability of random variable y being equal to 1 consists of 2 values of random variable x. So for some values there is only 1 point from random variable x which gets mapped to random variable y, but for other there are 2, hence the probability values of y are different from probability values of x. Furthermore, you should notice that these 5 new points have no visible relationship with the 8 points that we have for random variable x. Let's take another example, and this time the mapping is going to be non-linear but reversible. So it is 1 to 1, but it is non-linear. The mapping is y is equal to e raised to power x over 3, exponentiation of x divided by 3. So if random variable x takes on a value x1, then the corresponding value in the random variable y will be e raised to power x1 over 3. Since this mapping is 1 to 1, you can use either method to find the probability mass function of y. But the first method, where you take on the values of random variable x, map them through this mapping, get to the values of random variable y and assign them the corresponding values of probability mass function. If you use this method, then you can find the probability mass function of y, and this has been evaluated and shown in the slide. If you look carefully at this slide, you will see that the random variable x takes on probability values in a certain sequence, and that sequence is maintained in the random variable y. In the random variable x, the leftmost value is minus 4 with an associated probability value of 1 over 15. The corresponding point in random variable y is e raised to power minus 4 over 3, which is slightly to the right of 0 with an associated probability value of 1 over 15. Other points also occur in the same sequence going from left to right. But you should notice that in random variable y, points on the left side are close together, whereas points on the right side are further apart compared to the random variable x. This happens because this mapping, even though one-to-one, the mapping of exponentiation, is non-linear. It contracts points which are below a value of 0 and it expands points which are to the right of value 0 or e or 1. I'm not sure, you can find out. But certainly this mapping is non-linear. It contracts points on the left and expands points on the right. But there is benefit of it being one-to-one, which allows us to find the probability mass function of y quickly from probability mass function of x. The last example of transformation of random variable that we are going to discuss today is also from R to R, and this time we have chosen this mapping to be y is equal to 3 times sine of 2 times x. It is 3 sine of 2 into x. I have chosen this transformation with these coefficients of 3 and 2 intentionally to highlight a point. This mapping in general is many to one, but because the values attained by random variable x are discrete with gaps, if you transform this random variable x through this mapping, you will get 8 values. But there will be no sequence. There will be no sequence of random variable x getting related to the values of random variable y. This will be clear if you look at this slide. In this slide, on the top, you will see the original random variable x with associated 8 values and the probabilities. And in the figure below, you will see the probability mass function of random variable y, which is through a transformation of 3 into sine of 2x. You will recognize all the 8 values are being shown in random variable y, but they happen haphazardly, without any order, without any sequence, because the nature of this mapping, which involves sine, is not linear, is not even close to linear, and it maps the points in the range of x to points between 0 and 1, and once these points are mapped to points between 0 and 1, we multiply them by 3 because our complete mapping is 3 into sine of 2x. Hence, the points that we find in random variable y lie between minus 3 and 3. So it does not matter where the point lies in random variable x range, it will always be between minus 3 and 3, and the points in random variable x and points in random variable y will not have a well-defined sequence or symmetry or order associated with them. So we have talked about transformation of random variables, and we have talked about 4 examples of transformation of a random variable which is defined on real line to a new random variable which is also defined on real line. But we considered 4 different transformations to highlight points that for simpler and linear transformations you get easily to probability mass function of y from probability mass function of x. And for more complicated non-linear and non-invertible mappings, it is slightly more complex, but still you can come up with methods to find probability mass function of y from probability mass function of x. In last lecture, we discussed the expected values. If you have probability mass function of x, you can find expected value of x. And to find the probability mass function of y and its expected value, you can certainly go through this route, where you first find probability mass function of y and then use that probability mass function to find expected value of y. But you don't have to do that. You can get the expected value of transformed random variable from the probability mass function of original random variable plus the well-defined mapping. You can use that to find expected values of transformed random variables. Let's explore this idea a little more by considering 2 of the 4 examples of transformation of random variables that we just discussed. Let's find the expected value of the original random variable x, which takes on values at -4, -3 all the way to 6. If we find its expected value using its given probability mass function, we'll get it to be 4/15. Now, let's take the first reversible linear mapping that we discussed, that was y is equal to 2x plus 1. This gives us a random variable y, and if we take the probability mass function of this random variable y and find the expected value of y, we see that it comes out to be 23/15. Now, the interesting thing is, look at the mapping, it is 2 into x plus 1. Now, look at the expected value of x, which is 4/15. If we take this value 4/15 and fit this into this mapping 2x plus 1, you will get the same value, which is the expected value of y. So, expected value of y, which is 23/15, is 2 times the expected value of x plus 1, where expected value of x is 4/15. So, apparently, for this mapping at least, the mapping defines the probability mass function as well as expected value. So, if you know the expected value of random variable x, you can get the expected value of random variable y by just fitting this expected value in the mapping. Is it true for other mappings also? We can certainly find it out. Let's take the next mapping, which was y is equal to absolute value of x minus 1. With this transformation, you get a new random variable y with associated probability mass functions defined at only 0, 1, 2, 4 and 5. With this probability mass function, you find the expected value of this transformed random variable y, and it comes out to be 29/15. Can we get to this number by just fitting the expected value of x in the mapping? If we try that, we'll see that it is 4/15 minus 1 absolute value of the whole thing, which gives us a value of 11/15, which is not equal to the expected value of y that we get explicitly by using the probability mass function of random variable y. So apparently, this rule of getting to the expected value of y using the expected value of x and the mapping that defines the relationship between x and y works for some mappings and does not work for some mappings. It turns out that it only works for those mappings which are linear, of the form alpha times x plus beta, where alpha is a number and beta is a number, x is original random variable and y is the resulting new random variable. This is so because the operation of finding expected value involves summations, and summations distribute over the linear transformations, and it certainly does not distribute over nonlinear transformations. The next topic that we are going to talk about is conditional expectation, and this gets used a lot in probability theory. If you remember, we started talking about conditional events, conditional probability, concept of additional information the concept of reduced region of certainty, and we have gone through ideas like conditional probability mass function. All these ideas are related to some information being made available about otherwise a completely random phenomenon. So if additional information is given, then our perception about the likelihood of different values that this random phenomenon attains gets changed. And what happens to the other derived quantities under this changed perception? That is dealt with conditional probabilities, conditional probability mass functions, and today we'll talk about conditional expectation. One thing common to all this discussion is that when you provide some additional information in the form of some event having occurred, that event must have a probability which is greater than 0. Why? Because if a random experiment is performed and an outcome is observed, and this information is provided that something happened with probability 0, or something happened which was improbable, or it was not supposed to happen. So if the outcome represents something which was not supposed to happen at all, then it's meaningless to talk about conditional probabilities of other event on conditioned on this event which was not even supposed to happen. So in conditional probability mass function, and conditional expectation, the event which is the conditioning event which represents additional information should have a probability which is greater than 0. So how do you find conditional expectation? It's easy. You take conditional probability mass function of a random variable under the additional information, use that probability mass function and find your conditional expectation. In previous lecture, we have talked about an example of conditional probability mass function. The example was that you roll 2 dice and add the number of dots on the 2 top surfaces and get that number as your random variable. We found the probability mass function of this random variable without any additional information. Then we provided this additional information in first case that one of the dice is showing number 6, which gave us a conditional probability mass function. Then we provided this scenario where the 2 dice were rolled and this additional information was provided that none of the dice has 6 on top. So we have already found the probability mass functions for these 2 cases. Let's use the probability mass function of the original random variable, the unconditional, and conditional probability mass functions of these 2 cases and find the expected values, unconditioned and conditioned on these 2 events. These expected values can be found explicitly by using all possible values in conditional probability mass function. Let's find that, and for that we have to look at that slide again, and in this slide you will see that the top figure shows the unconditioned probability mass function of the random variable x. It takes on values from 2 to 12 with probability associated with value 2 being 1 over 36, probability associated with 7 being 6 over 36, and probability associated with 12 again 1 over 36. If you use all these probability values of 1 over 36, 2 over 36, 3 over 36, etc., etc., and the values this random variable attains, you get an unconditioned expected value of 7. This should be no surprise, because if you look carefully at the probability mass function of this random variable, it is symmetric, and you know that expected value is a point where if a rigid rod modeled with weights hanging equal to the probability values is anchored and becomes stable. So because this probability mass function is symmetric, the only point where it can be anchored and still the rigid rod is stable is the central point 7. So you can use explicit calculations using probability mass functions and probability values to get to expected value, or you can carefully analyze the probability mass function and graphically see where the anchor point should be so that this model is stable. So unconditional expected value of this random variable is 7. If no additional information is provided and you roll 2 dice, then on average you expect the sum to be 7. Let's look at the first case where some additional information was provided. And the information was that one of the dice has 6 on top. When you provide this information that one of the dice has the maximum possible number on top, then you are favoring higher values of the sum. If this information was not provided, then that particular dice could have had 1, 2, 3, 4, 5 or 6, but with this additional information that 1 is 6, you are favoring higher values. Now you expect the sum to be higher because one of the dice is already assuming the maximum possible value. This is clear if you look at the central figure in this slide, which shows the conditional probability mass function for this case, which starts at 7, ends at 12, and attains probability values of 1 over 6 for 7, 8, 9, 10, 11, and 12. And how do you find the expected value of this conditional probability mass function? Again, use the graphical argument and you will find out that the expected value of this conditional probability mass function is at 9.5. So as expected, now the expected value of this random variable with the additional information that one dice is 6 has gone from 7 to 9.5. Let's look at the other conditioning event where after 2 dice were rolled, the information was provided that none of the dice is having 6 on the top. As you can feel, with this additional information, you expect the sum to be lower. Now you are excluding both of the dice from having the maximum value. So the maximum value each dice could now have is 5. It can take any value from 1 to 5. The other can take value from 1 to 5. So you expect sum to be less. How do you find that expected value? Just use the probability mass function, the conditional one for this case. Look at this slide and see where it should be anchored so that it becomes stable. Of course, it is 6. Now, the expected value of this random variable with this additional information that none of the dice is 6 gives an expected value of 6, which is smaller than the unconditioned expected value of 7. So, additional information provided in the form of conditioning events change the expected value of a random variable. One last point about these expectations, conditioned and unconditioned, is that the expected value of a random variable is just a number. But conditional expectation conditioned on some event can be a random variable. How? Imagine the conditioning event not being fixed, but a variable event parameterized by a certain parameter, say t. With this t as a parameter, we can define a collection of conditioning events. For example, a conditioning event parameterized by t could be that the random variable lands between 0 and t. As t varies, this conditioning event varies, and under this new variable conditioning event, we can find the expected value of the original random variable. So as t changes, the expected value also changes. So this value of conditional expectation becomes a random variable. It takes on real values on real line as a parameter of t. Hence, you can consider conditional expectations to be a number if the conditioning event is fixed, or if conditioning event is a parameterized variable event, then this parameterized variable conditional expectation can be considered as a random variable. The last topic in today's lecture is the concept of covariance and related concept of correlation. So far, we have found expected values of random variables which were defined on real line, or expectations of random variables which were transformed from this random variable defined on real line to a random variable also defined on real line. Or we found conditional expectation where conditional probability mass function was also defined on real line. But you know, there are joint random variables, two random variables jointly defined on an underlying sample space, where once the experiment is performed and outcome is realized, then two values are generated simultaneously, and we usually put these two values on a two-dimensional plane by putting y and x-axis and putting one observation on x-axis and the other observation on y-axis. And if these values attained by two random variables jointly are finite, they get mapped to a few points on this two-dimensional plane. And two-dimensional probability mass function is also defined on those points as vertical lines representing the probability associated with that point. Can we use that to find joint expected value of two random variables which are jointly defined, which get realized jointly when the experiment is performed? The answer is yes, but you have to be careful. If you remember that lever analogy that we used when we were finding the expectations of variables defined on real line, in that we said that expectation of a random variable is the net torque when a rigid rod is taken and it is anchored at 0 and few weights are hanged on this rigid rod. The location of the point where the weight is hanged is the value attained by random variable, and the amount of weight placed on that point is either equal to the probability of random variable being equal to that, or a number proportional to that probability. If we have such an arrangement, then the net torque on this rigid rod is the expected value of a random variable defined on real line. And a further analogy was that if we move the anchor point to a point which is the expected value of such a random variable, the rod nicely balances itself and it does not tilt to either side. Can we extend this analogy to two-dimensional jointly defined random variables? The answer is no. One could wish that if we have two random variables defined jointly on a portion of two-dimensional plane, then one can imagine this plane being a rigid sheet of metal and few weights hanging at points x1, y1, x2, y2, and this plate being anchored at some point. This analogy does not work. For once, even if we are taking this joint distribution and two random variables jointly defined, they will give an expectation, an expected value which will be a number, a one-dimensional quantity. So you cannot move that anchor point to that one-dimensional quantity. The reason is every point on that sheet is a two-dimensional vector. So if you anchor this sheet at origin and hang these weights, this analogy is not going to work. So I advise you not to think in terms of a rigid sheet and weights when you are thinking about two random variables jointly defined. So having cleared this, let's find the joint expected value of two random variables jointly defined which have a joint probability mass function. Of course, if they have a joint probability mass function, they have their own marginal probability mass functions for x and y respectively, which can be obtained by summing all the probability values along rows or along columns. So if we have two random variables jointly defined with an associated joint probability mass function, we can find the joint expectation or E of x into y as summation of multiplication of all joint probability mass function values and the associated values of x and y. So it is summation, double summation actually, over the variables values attained on x-axis and attained on y-axis, and all the values x and y multiplied together and with the associated probability. So you can see in this slide that this expected value takes on a double summation and it gives just a number. Of course, from this joint probability mass function you can find marginal densities, the probability mass function of x and probability mass function of y. You can use those to find expected value of x and expected value of y. You know that if you have two random variables x and y and you define your random variable z as x plus y or x minus y, then expected value of z is equal to either sum of expected value of x and expected value of y or the difference depending upon whether you used z is equal to x plus y or x minus y. Once again, expectations involve summations and summations are distributed over linear combination of random variables. But the question is, can this be extended to multiplication? In other words, we have two random variables x and y and we have found their joint expectation, which is expectation of x into y. Is it equal to expectation of x multiplied by expectation of y? The answer is in general no. And there are special pairs of random variables which do not occur very often where this is true. That is, expected value of x into y is equal to product of expected value of x and expected value of y. If the two random variables do satisfy this property, they are said to be uncorrelated. And this is captured in the quantity which is called covariance. So what is covariance? It is expected value of x into y minus expected value of x into expected value of y. If this quantity is 0, then they are uncorrelated. And if this quantity is not 0, then this is the covariance of the two random variables x and y. So usually this covariance is not 0, but if in certain special circumstances this is 0, then random variables x and y are said to be uncorrelated with each other. A related quantity is correlation coefficient. If you have two random variables and you have found their covariance, then you divide this covariance by square root of multiplication of variance of x and variance of y. You can see the formula in your class handouts or in your slides, but the important point is that this correlation coefficient is a dimensionless quantity and it always lies between -1 and 1. For real world random variables which are somehow related to each other, which are not independent of each other, the correlation will be somewhere between +1 and -1. And it will be exactly equal to 1 for those two random variables which are linearly related with each other. And it will be -1 for those two random variables which are linearly related with each other but with a minus sign. So if one random variable takes on bigger values and the other also takes on bigger values and the two values are related to each other with a linear equation, then the correlation is 1. Similarly, if one random variable is taking positive values, the other is taking negative values, and the two are related with a linear equation with a minus sign, then the correlation coefficient of these two random variables will be -1. All other random variables have correlation coefficients which lie between -1 and 1. And there are special pairs of random variables which have a correlation coefficient of 0. Those are uncorrelated, where the covariance is equal to 0. To summarize what we have covered, we have completed our discussion of discrete random variables and application of elementary probability theory principles to discrete random variables. We have covered their distribution functions, their expected values, their transformations, and other related quantities. I hope you have a good grasp on these underlying principles of probability theory, and starting from next lecture, we are going to apply these principles to those random variables which are defined on uncountably infinite sample spaces. So those random variables will be continuous valued, and to apply those principles you will need good understanding of calculus, particularly differential calculus. So enjoy your class handouts and textbooks, study these principles, apply them to real life problem, and get a good feeling of what probability is and how it is applied on real world problems. Starting from next lecture, we are going to start the treatment of continuous random variables. Till then, I wish you the best. Thank you. Khuda Hafiz.